Hi, welcome to Mr. Marvoli's second screencast. Today what we're going to take a look at is we're going to go ahead and take a look at exponential growth and decay assignment. Now you guys during this period will have been working on this front page. This front page requires you to put 100 individuals in your cup, pour it out. On one side is S, means they unfortunately didn't make it. On the other side, if it is blank, that means they did make it. Now in essence they have a 50% chance of making it or not. So this brings us to our next point, which is I'm going to go ahead and walk us through the formula part. Okay, number 5 through 8. You guys should have done 1 through 4 based on your experiment, and I'm just going to help you set you up through this second part of the assignment. Now number 5 gives the formula for exponential growth or decay. And here's the formula. Basically what we're going to be doing is we're going to be solving for y. A is your starting value, just like your A of 1 when we start our geometric sequences. That's going to be our starting value. Our B is either our rate of growth or rate of decay. In this case, people aren't making it, so is going to be the rate of decay. So what could we say the formula is for this example? So we'll say this formula represents the amount of survivors based on the number of years. And that's essentially what we're trying to figure out, is how many people will be surviving after a certain amount of time. So in this case, we're going to go ahead and set up a formula for it. So it already gives you a formula, but we're going to go ahead and plug in our values. So I'm going to go ahead and backtrack a little bit. So for number 5, our formula is going to be y is equal to, again, A is our starting point. How many people do we have? In this case, we have 100 people. That's what we're starting out with. That is my starting value. If we're starting out with more people, then obviously that will change. Now, when we flip the paper values out of the cup, it has a 50% chance of landing on one or the other. So our rate is going to be 0.5. Now, the reason why it's 0.5 is it is technically 50%, so it's actually technically 50%, but we can't put 50% in there. We have to move from 50% to a decimal amount. Anytime I move a percent to a decimal, I have to move my value twice to the left. So I'll move it twice to the left. I will have a little decimal there, so it is 0.5. I'm going to go ahead and leave it at that. Now my x is going to be my time, and that's raising it to this power. So on the power button, we should be able to raise it to a certain power, and that would be going right here. For if I want it for 2 years, I would put 2. I'd be raising 0.5 to the second power. If I want it for 3 years or 4 years or 7 years, I would raise that to that power. So it makes it a little difficult in order to do that, but I'm going to go ahead and put a little arrow up, and that's going to represent my power, my number of years. So in this case, I did it for 7 years based on the pattern that you guys had. You guys did it for 7 years. So normally T would be the number of time, but based on your experiment, you did it for 7 years. And that should give you approximately what it should be. The result should be at the end of your experiment. They should be pretty close to one another. Now, number 7 says if it actually took 10 years to develop a cure, how many people would survive? And again, you can do the experiment, but we want to go ahead and do this mathematically. So we're going to say 100, and then I'm have 0.5, and I'm raising that to the 10th power. So now instead of 7, I'm going to go ahead and put 10. Now in order to solve for that, I want to go ahead and use a scientific calculator. Here's a scientific calculator. So before I can go ahead and before I can go ahead and multiply these two right here, my order operation says I have to use an exponent first. Please excuse my dear Aunt Sally. The P is parentheses, the E is exponents, and the M is multiply. So before I can multiply, I have to raise this power. So 0.5, and we're going to go ahead and raise it to the 10th power. So 0.5, and on some calculators it's going to be y to x. Some are x to the y. We're going to hit this button, and we're going to raise it to the 10th power. There we go. And now we're going to go ahead and times it by 100. So once I've raised it to that power, let me backtrack a second. Once I've raised it to the 10th power, now I can go ahead and multiply these two values. which what I'm going to go do, I multiply by 100. I hit equal, and there's basically a, if I were to move my value over, this is basically a very small chance of anybody surviving at that point. So based on the number of survivors, it'll be 0.09. So we're sitting around a 0.1 survivors left at that point. So not great odds in this case. So we'll say 0.1 survivors. So not great odds of someone surviving. So basically 1 out of 10 chance of having a single survivor after 10 years. Oops, that was probably the wrong spot. Here we go. And the last part in here is just going to be how much for 5,000 survivors after 7 years. So we're going to go ahead and do the same thing. We're going to go to my scientific calculator, and there's a 50% chance. Now I'm going to go ahead and raise it y to the x, or x to the y, and I'm going to raise it to the 7 because it's 7 years. So I'm going to go ahead and plug in 7 into my scientific calculator. So I'm raising it to the 7th power. And now I can go ahead and multiply. In this case, it's no longer 100, it's 5,000. If the initial population was 5,000, how many would survive? So now we're going to go ahead and times it by 5,000. And there we go. We basically have 39 survivors. So we can go ahead and answer it by putting in 39 survivors. I hope this helped, guys. Again, this is to kind of help you guys out for the second part of the assignment. If you have any questions, I'll let you guys go ahead and do number 9, same exact steps of what we just did. And if you guys have questions, let me know. Thanks.